from anyone. All right, please unmute yourself. Everyone, unmute yourself. Mizuko Bwanji.
Kazuka Bunogai.
Oh, thank you. Thank you for coming. Um, I'm going to get started with a couple of thoughts. I just finished this. I worked on it from 1 in the morning until 6 o'clock. So I hope it's good. Let's see. Let's get rid of all of these things. Whoops, there's Eddie. Okay. There we go. All right, so there was a lot of preparation. There was a podcast from MIT's Jacopo Buongiorno, which means good morning. It means Mazuka Buongi in Italian. Uh, and I liked him because he wasn't really super advocating nuclear. He wasn't saying nuclear is great. And yet he gave a very balanced argument. I hope it was appreciated by you. If you didn't hear it, please go and hear what he has to say when you have time this weekend, maybe. And then there was a lot of readings, and we're going to go through them a little bit today. And the big questions for you for this class is we're going to go through all these technologies, and I'm going to want you to describe the major recent advantages in those technologies, and then describe the state of readiness. In the syllabus, I said you want to rate them as we're already doing it. It's a near certainty it's going to work. I'm not sure about it versus it's a fairy tale. It's never going to happen. And I want you to start by being honest here and tell me how much of the preparation you did. We're going to have a poll, and which number describes, like you watched everything versus 5, you never even looked at it. Okay? Everybody, please vote. We have 19 people out there. So I want to see 19 votes. I've got 8. I want everyone to participate. We got 13, 14, 5 more. Here we go. All right, that's enough. Share results. So we're all over the board, and I think you're going to find that the people who prepare are going to gain from that. Okay? But so let's jump in now. We are experiencing a nuclear renaissance. 20 years ago, I was kind of anti-nuclear. 10 years ago, I told my students that, oh, I was anti-nuclear, and so were a lot of people. And 10 years ago, the issue of climate change and the awareness of the safety of nuclear promoted nuclear a lot more, made people much more open to the idea. That's not nuclear that's dangerous. It's carbon dioxide and pollution. But even 10 years ago, I told my students, you can advocate for nuclear, but don't study it because nothing's happening in that field. And I spent a year in Berkeley, and I can tell you the nuclear engineers were very frustrated people. Why? Because for 40 years, they had been studying nuclear and their knowledge was constipated, right? Because they couldn't push out a nuclear reactor because after Chernobyl, nobody was willing to commit to nuclear. And that's all changing now. That's changing because things we talked about yesterday, people are aware of the dangers of air pollution and climate change. and they're aware of how safe nuclear is. And now we've got a whole bunch of knowledge because people have been studying it for 40 years. These small nuclear reactors, SMRs, this is a picture of one being deployed. So what are they? They're smaller. Diablo is 2 gigawatts. These are as big as half a gigawatt, but they go all the way down to 1 megawatt. So 1 megawatt would be enough for like a village, even a large village. The modular construction allows them to be produced in one area. And so you can get economies of scale, and it should bring down the costs and reduce the amount of time it takes to build one because you just build it, you're building them constantly, and you just pick one up and put it in a new location. I mean, it's not that simple. You have to lay concrete and all the other stuff. But I want to tell you, yes, we are deploying them. They already are running, but they are not cheaper than regular nuclear facilities yet because they're so new. So there's a learning curve that things get cheaper over time, and we just haven't gotten to that yet. So time will tell if modular construction, if the SMRs really do wind up being cheaper than conventional nuclear. They use passive control, so there's inherent instability. It doesn't require people to be constantly controlling control rods. There's no external power source required. They power themselves. If that doesn't seem important, remember Fukushima. What happened with Fukushima, the nuclear reactors were not damaged by the tidal wave. What happened is it knocked the power out, so there was no electricity power to pump the cooling pumps. Does this seem crazy to you? It was a nuclear reactor generating electricity, but it couldn't generate electricity for itself. So anyway, SMRs are going to do that. And they're portable. This is good for two reasons. One, you can make them in one place and ship them out. And two, they can move around themselves if they have to. That's particularly important for ships. So maybe you know this or you're surprised to find out the very first nuclear reactor was put in a submarine. It wasn't even on the ground. And you say, why did they do that? It's not easier. No, it's much harder in a submarine, but it's much more important in a submarine because submarines rely on stealth. They rely on being underwater where no one can detect them. But if you're powered by fossil fuels, you need air. You need oxygen to drive the engines. And so nuclear subs, when I went to grad school, one of the guys, Hans Hermann, you can look him up, he used to be the skipper of nuclear subs, and they'd go underwater for months, drive you crazy. But they can do it because they don't need oxygen to burn the engine, right? They just use nuclear. So anyway, the first nuclear reactor was on a sub. And if we have small modular reactors, we can put them on boats, in particular, shipping containers. Shipping uses 2% of our energy and produces 2% of climate change gases, of greenhouse gases. And so you could put a nuclear reactor on these and drive them without fossil fuel. I mean, it's important for ships, especially because we can't run an electrical line to the ship, right? And so if there's a nuclear reactor that's small enough that can sit on the ship, these intercontinental ocean transport can be fossil free, emission free. Okay, so what are the challenges? Okay, they could be cheap, but we don't know. They're still more expensive than conventional. They still are going to have regulatory challenges. When you put one in, there's going to be a whole lot of people who don't like it there. There's going to be a lot of paperwork. You still have the same proliferation and waste problems. Actually, probably more, because now you have small reactors in a whole bunch of places, especially in ships if you do this. So Navy ships are one thing. They have a lot of guns. But container ships are routinely captured by terrorists. And so now, if you had nuclear reactors on them, when someone captures a ship, they capture a nuclear reactor, which should concern all of us. And I want to spend a little bit of time on the competition because everything's a comparative measure. We could make nuclear work, but the alternative might be renewables. And let's look at this. How about solar? When I was a kid, a 100-watt solar panel costed $10,000. So this is a log graph, a semi-log graph. So when I was a kid, 1975, $100 a watt. So a 100-watt solar panel was $10,000. And now this has continued to drop. It's now 10 cents a watt. So it's gone from a 100-watt panel has gone from $10,000 to $10, a factor of 1,000 decrease. You look at two areas of this graph. The first decrease was caused by scientific progress. The second decrease was when commercial progress kicked in. So this is computers being important. Well, when they started mass producing solar panels. And we can try to put a line fit to this. And we have, come on. Every 10 years, the cost decreases by a factor of 10, right? How long will this continue? Well, a number of people have told me in 2000 that this could never continue, and it keeps on dropping. So we'll see. But in any case, right now, solar panels are essentially free. The cost comes from putting them in and running the wires. And then you say, oh, well, that's very cheap. Maybe the cheapest electricity there is, but that only works in the daytime. But then you look, batteries are also decreasing at the same, not the same rate, but we can fit a line to this and see that every 10 years we get a factor of 4 decreased. And this is being driven by the electric car market mostly. Initially, it was computers, and now it's the electric car market. So when we think about making that 50-year commitment to nuclear energy, we want to keep in mind the competition is getting stronger and stronger and stronger. So how about putting a nuclear reactor in a hole? Great idea? Maybe, maybe not. You don't have to worry about a containment vessel, right? Meltdowns present little problem because they're already underground. And waste and proliferation is not a problem because they always stay underground. So the nuclear waste would just stay down there. And then when you're done with it, you just bury it. And you say that's dangerous. Well, you have a big hotspot way down in the earth, which already was hot anyway. So maybe it's fine. So why don't we do it? Well, they haven't done it yet. We don't know how much it's going to cost. There are uncertainties with the geology, right? Like what kind of rocks we'll run into. How are you going to manage the heat? Because you have to get the hot water up to the surface to boil. And how are you going to prevent it from getting too hot down there? We don't know how we can maintain it. And so these are all things that we don't know about. They're the unknowns, but they're the known unknowns. But there are also unknown unknowns, things we don't even know could become a problem because we've never done this before. So a friend of mine called me up and said, hey, I have some money and I can invest in this technology, in this company. What should I do? And I said, it could win big if they win, but I don't think so, right? All right, so how about thorium? Thorium is great because, well, I don't know if they're great. I mean, I think they are. The company, I liked the talk I saw that they use thorium with a little bit of 235 because you need the 235 to produce the neutrons to get it started. They construct it in a shipyard and they ship it on big ships. So they don't have to be really small. And they only service coastal cities. right? Which is no big deal because a lot of people live on the coast, right? So we won't have them in Malawi, but Singapore, perfect. And they sink them. They sink them into, I don't know, several meters, 10 meters of water. So we love them because thorium is inexpensive and abundant. It's difficult to turn into a nuclear weapon. You can easily transport them to coastal cities. They produce less radioactive waste, and they're inherently safe for two reasons. One is it has passive control that keeps it, running. And it turns out that they run the fission. It's all in liquid form, and it requires being in the reactor chamber to have the chain reaction. So if there's a problem, there's a plug that thaws. If it gets too hot, this plug thaws, and all of the nuclear fuel drains into another tank where it can't fission. And so this is, there are a lot of safety measures that are good. And so why not? Well, it just remains to be seen. Okay. So then you say fusion. We've already talked about fusion. What is the big innovation here? If you look at it, the big innovation is that we can make them smaller because now we have the strongest magnetic fields ever before. So if they're real strong magnetic fields, we can confine the plasma and we can increase our NT tau triple product, right? How dense we can force that plasma. And so maybe this is the answer. And you heard me say it's way more complex than fission. I mean, you start out with a vacuum, which is already impossibly hard, right? And now, I began a PhD in plasma fusion. So I did my master's in it. And I said, fusion will remain the energy source of the future. It's never going to happen. There will never be a today for it. It's never going to be inexpensive enough. But, whoops. But there's already a company that's invested in this, which means there are people with a lot of money that believe this is the right way to go. So how did they know that? And we know there are many people that know way, way more than me about fusion. And they're saying it's going to work, right? Like Dennis White. And so then the question is, I dropped out of that program or switched out of that program 30 years ago. Who do you believe, me or them? And it's a tough one, really. It's not, you're laughing at me. Look at this guy. This guy is laughing at me. Yeah. Because there's two things. One, having been in academia, right? When you're studying fusion, that's all you think about. You want it to work so bad, right? I don't trust them when they say it's going to work. And venture capitalists, and now I'm not a venture capitalist, right? If you give me $1 billion, I'll become a venture capitalist. But a lot of them are committed to try something new, right? There'd be a huge payoff if this works, and maybe they're interested in it. So it's okay. I don't want you to believe me. I just want you to hear what I have to say. Make your own decisions. And if you prove me wrong, I buy dinner. Okay? So look, this National Ignition Facility, NIF, they win the contest for the best picture, don't they? Right? But they're not going to win an argument that their technology is simple. That's a huge undertaking. And so let's understand what inertial confinement fusion is. We talked about it before. Is you have this blue stuff is fusile material, is tritium and deuterium, and it has a heavy metal outer layer on it. And you blast it, the bejesus out of it with huge amounts of laser power. And what it does is it kind of explodes the outer shell and compresses the fusile material. And then it fuses and you get a thermonuclear burn. Okay? Now they're celebrating their success. What is their success? They put in 2 megajoules of laser power, of laser energy, pardon me, and they got out 3 megajoules of fusion energy. So just give us, remember, 3.6 megajoules is a kilowatt hour, right? So that's the energy in like a car battery. Okay. And so you say, hey, that's great. We put in 2 megajoules and we get 3 megajoules out. So that's a gain of 1.5. But wait, it's actually better than that because the energy you get, it's not energy laser divided by energy or energy fusion divided by energy laser. It's the energy out divided by the energy in. And if you put in 2 megajoules, you get those 2 megajoules back out again. So the total heat produced is 5 megajoules. So now we have a multiplication factor of 2.5. And you're very happy about that. Until you realize that laser energy isn't the same as thermal energy. Where did that laser energy come from, those 2 megajoules? Well, it turns out those lasers are less than 1% efficient. Oh. So therefore, to get those 2 megajoules of laser, you needed 300 megajoules of electricity. Right? Now, our gain factor is pretty low, less than 1%. But electrical energy is not the same as the thermal energy that you produce. That electrical energy had to be produced by a Rankine cycle, let's say, which is only 30% efficient. So our yield is about 1/400th. So they have a factor of 400 to go before they really have break even. That is, thermal energy out is equal to the thermal energy we put in. And then you can do a quick calculation of how close are we to generating anything with this. They only got 5 megajoules out. And if we want a gigawatt facility, we're going to have to blow up 200 of these every second. Now, if it's just a megawatt facility, you get by with, every 5 seconds. But you looked at the size of that thing. Are you going to build something that big to produce a megawatt? Right? So the people writing that article would have you believe that inertial confinement fusion is right around the corner. And you draw your own conclusions, but in my game, that's still fairy tale. A bullet, you decide. No, you rely on me. What you're doing here, this is physical pressure. Physical pressure is caused by the compression of the electron shells around the atoms. Okay? And what you're doing here is you're looking at that electrostatic force to force nuclei together, nuclear forces. And I just don't think it's going to happen. Even the people doing it, I don't think are very sure. But it's great. I love that they're trying it. So, wow, this went very quickly. I hope you're not disappointed that it's almost over. I want to leave you with this idea, though, that nuclear is great, but you're looking at a 50-year commitment. And renewables continue to become more and more compelling. It's even more important that you recognize like solar and wind, right? But solar still only produces, I don't know, like 3 or 4% of global electricity. So we're not innovating solar as much as we could be because it's a small part of our concern. As it grows, it's going to get better for that reason too. There's one more thing I want to say about commitment. When you make a 50-year commitment, you're not just committing to the nuclear technology, you're also committing to the fact that you're going to have big central station, like and grid. And one of the things we're finding like in California, the grid is very expensive because it causes wildfires. Solar electricity will get cheaper and cheaper and cheaper. The grid will not, because you have to put the same amount of copper down. All right. And so you're making a commitment to the idea. If you commit to nuclear, you make a commitment to the idea of big grid electricity. I'm not convinced of that. And there's another assumption that we're making, all of us, all the time, is we're making assumption of global political stability. We're making an assumption that France isn't going to decide it needs nuclear fuel and just come down, kill a bunch of people in Malawi, and take all of our nuclear fuel. Now you say France would never do that. I think France would never do that, right? We also think France would not, or Germany would not just grab a nuclear container ship and steal the nuclear reactor. They shouldn't. This is the global order that we have, that we've become accustomed to. But are we sure that global order is not going to change? We've made an assumption based on the last 80 years of peace after World War II. We've worked very hard to keep that. But if all hell broke loose, would you rather have a nuclear plant with big grid, or would you rather have the solar panels on your roof that you could just pick up and run with? So I'm going to leave you with that. And thanks for your attention. So I'm going to slam you guys all into breakout rooms, and you're going to talk about what we learned. And I'm going to come and visit, and you're going to give me some questions. Can you do that? Okay, you're all going to unmute yourself. Here we go. Great. So welcome back, everyone. I think the discussion was good. One group was talking about politics. Sorry, I ended on a political note. Maybe that sends everybody in the wrong direction. At the same time, you got to mute yourselves. At the same time, you know, politics is a part of the reality of our situation. And you know, I mean, one of the things are, you look at Ukraine. Russia is trying to cripple Ukraine. What do they attack when they try to cripple Ukraine? They attack the power centers, right? That's where they send all their bombs right away. And, you know, nobody has electricity. You have to mute yourself, everybody. Okay? Thank you. Yeah. I don't know why I can't mute you. It's all right. The one question that came up in every group was you didn't understand, or you wanted me to repeat this same energy calculation for inertial confinement fusion, right? They're claiming a gain of 1.5. And I even said you could say 2.5 because the heat that you put in, you also get out on top of the fusion energy. But the thing is that you can't say we put in 2 megajoules of laser and we get 5 megajoules out. How did you get that 2 megajoules of laser? Well, you had to generate electricity to do that. And you need to generate a huge amount of electricity to get that laser, because these lasers, not all lasers, these lasers that produce this X-ray compression are very, very inefficient. So in order to get those 2 megajoules of laser power, of laser energy, you need 300 megajoules of electricity, right? So that's like on the order of 100 kilowatt hours. But how did you get that electricity? You had to generate that with something. Now you could say we generated with solar, and I'm like, no. That's cheating. You should say we generate it with the same product that we get out. So we get out 5 megajoules of thermal energy. And how do we generate electricity with thermal energy? Well, we use a Rankine cycle, right? We boil water, and that's about efficiency of 1/3. And so, yes, it's true that 2 megajoules of laser gives you 5 megajoules of thermal energy when you add in the fusion. But you had to put in 900 megajoules of thermal energy to get those 5 megajoules of thermal energy out. And so, yeah, it's very nice that they got more energy out than they put in this other form. But if what they're saying is this makes it a viable energy source, that is a lie. They are lying, right? Their words aren't lying, but the message is not true, and they know it. Okay. So there you go. That's the only question I had from you guys. So I think I'm going to end class. Oh, wait. So tomorrow's going to be great. We're going to talk about Malawi. And I have 2 videos for you to watch and 2 things for you to read. I want you to do it before. Now, I set up a new video watching platform. It's going to take me an hour or so to get it set up. So we're going to try just like WeVideo, only this is hopefully better and simpler. So I'm going to be able to record if you watched, and I will count that. They're 2 short videos. Make sure you watch them. Okay. And you'll like them besides. They're great. They're great. Okay. So I'm going to send that out along with the video from today's lecture. I'll send that out in a couple hours. Okay. All right. All right. So class is over. What do I say at the end? You just say bye-bye. How do you say in Chichewa? Do you just say bye-bye?
Tionana.
Teolala. Tiondala.
Tionana.
Try again, Christina, again.
Tionana.
Tionana.
Yes, great.
So Tionana, but I'm going to stay.
I'll see you tomorrow.
Oh, certainly. I'll see you tomorrow, right? But I'm going to stay so we can talk some more and we can go over the Excel spreadsheet if you want to. Tionana. Got it. All right. So, should I bust out the Excel spreadsheet? Do you want to do some of that?
Yes.
Yes.
Okay, because if you don't want to, I'm not gonna, I don't need to do it myself, right? So here we go.
Let's go through it once more.
Yeah, thanks. All right. So this graph, I can just go here and double click on the point, right? And it'll tell me what I'm graphing. This is my balance in my bank account. Hey, somebody's making noise here. Now you mute yourself, you guys. No. James, you're making a whole bunch of noise. Yeah. All right. By clicking this, right, we find that what I'm graphing is I'm graphing the amount of money I have in the bank versus the year. And then you say, okay, well, how did I find out what I got in the bank? How much money did I get in the bank? So you can do this all the time for a spreadsheet. You don't need me to show you what to do. Is I take whatever I earned whatever I had before in the bank, that's my previous balance, and I add to it whatever happened last year, right? So the money I have now is the money I had last year, plus or minus whatever change there was this year. And then you say, okay, how did I get my previous balance? Oh, my previous balance is just, let's do this again. F6. Oh, okay. That's the money I used to have plus the interest rate, right? Because there's a 10% interest rate. So if I'm in debt, if I was in debt last year, I'm a little more in debt this year. If I had money in the bank last year, I have a little more money in the bank this year, right? Okay, and the balance, what's the balance? The balance is everything that I earned last year minus, everything that I earned last year, the revenue, minus the costs. I don't know, am I, having a hard time with this, sorry. Yeah. I should find a way to make this a little bigger. Oh, here we go. Does that help? I don't know why we're having these problems, but I mean, we can see, right? So yeah, the balance from this year is whatever I took in last year minus whatever whatever the costs were. And then we go to the revenue. How do I find out how much money I made last year? We double click here, and it's the amount of electricity generated times the amount that I charge per kilowatt hour of electricity, right? And how about the cost? The costs are going to be calculated right here, the annual costs every year, okay? And so then we go, well, how did I calculate costs? The calculated costs are F3 is the maintenance, like the janitors, the people who clean, the facility, times E3 plus B times B6, right? So the amount of electricity I generate times, hold on. B6 times E3 is operations, right? So this is the amount of cost that you have per kilowatt hour of electricity. And you say, well, where did that come from? Oh, that's the cost of fuel, right? So it's how much you spend for fuel per kilowatt hour. And maybe you change it because of some other factor, and you multiply it by the number of kilowatt hours that you generate every year. And so that's how you get your cost. And let's go back to revenue. So revenue is the price you pay per the amount of kilowatt hours you generate. And this we pick, but this is a matter of how much power we put out and what the duty cycle is, right? And the number of hours in a year, okay? So the capital cost is important because that's the initial cost that we have. That's what gives us an initial negative balance because we start by paying a whole lot of money. How do we calculate that? Well, it's the size of the facility times the cost of per watt, right? And like we said before, if it's solar, you could probably put 50 cents a watt because the solar panels are 10 cents a watt, but then you have to like put them in the, you have to install them. But if it's nuclear, it's going to be on the order of $10 a watt, between $5 and $10 a watt. Okay, and so you can change the interest rate. The interest rate is important because that's what determines the change in balance from one year to the next because of debt. The efficiency is important because that calculates the amount of energy we generate every year, right? Actually, it's kind of the inverse is when we talk about the fuel costs, right? That's a capital cost, pardon me. When we talk about the operational costs, what we do is we take the amount of energy we're generating, B6, and we divide by the efficiency. Because let's say the efficiency is very low, and this is what that whole argument about the inertial confinement fusion is about, is the efficiency was tiny, tiny, tiny for producing lasers. And so if you look at the fuel you need for those lasers, where you take the energy of the lasers, but you have to divide by the efficiency, because that tells you how much fuel you have to put in. So hopefully this all makes sense to you now. Do you have questions about it? There we go. Longi.
Yeah, sorry, I'm suffering. So I was not able to. Are you hearing me?
I cannot hear you. I mean,
Are
I
you
can
hearing me?
hear you, but I don't, it's all muffled.
Okay, so yeah, probably. Maybe I will just meet you in person tomorrow.
Well, what you could do is you could write your question into the chat. Click on the chat and write me a question. Anyone else with questions on that? And what I really like is yesterday, someone said, can we use this for calculating costs of other energies? Yeah. And and you can. And I think it's a great idea. You could even use it to calculate the cost of driving to San Francisco, right? It would just, you'd have to put in different things. Okay, so you asked, Longe, you asked, how do we calculate system efficiencies? And that is just determined experimentally. Okay, I mean, we could calculate them theoretically, but that's not what we care about. We care about how it actually works. So these are things, Longe, that you need to learn. Like, I mean, this is what I'm teaching you here is 1 week of my advanced energy class. And that's like week 6 out of 10. And in the first week, the first 2 or 3 weeks, we talk about, energy flow and efficiencies. And so a Rankine cycle where you boil water, they typically get 30% efficiency. A Brayton cycle. Do you know what a Brayton cycle is? It's a jet engine or a gas turbine, right? So gas turbines get about the same. They can get a little bit better. A Brayton cycle might get up to 40% efficiency. But what you can do is you can use the exhaust of a Brayton cycle to boil water, and that gives you a combined cycle. And together you can get over 60% efficiency. Solar panels are about 20% efficient, but we don't really care because we care about efficiency when we have to pay for the fuel, but sunlight is free. So the cost of solar panels are buying the panel and the real estate. Like, do we have enough roof space or do we have to buy a forest? Okay, we got a question from Rogers or a statement. I would like to attempt to build this Excel sheet from scratch. Do you have some reference materials? No, I don't. I don't. Um, But what I would say is start building and see what happens. Yeah. I mean, if I were you, I'd just give it a try. Just do a very simple model. Um, if you need some help, you could Google building a financial model with an Excel spreadsheet, see what it says. But in general, when people work with computer models, you rarely build anything from scratch ever, right? Like if you're working with some computer model, you just tell somebody, give me what they did before. And then you figure out how it works and you change the parameters to make it work for you. So Rogers, um, I want to tell you that your question is wrong, right? I can understand wanting to build something from scratch. I would love to build a bicycle from scratch, right? But that's not the way it's done. And why would I make it harder for myself? There's steel tubing everywhere. Why don't I just get some steel tubing and weld it, right? And so you don't need to put yourself through that. Get yourself a model and start changing it, and you will learn how to manage this. Where does NPV factors come in? NPV, what does NPV mean? Net present value. Um, yes, that has to do with correcting for inflation and stuff, right? Yeah, I didn't include that in this model, but you can just change the interest rate to indicate that, right? Um, Yeah, we also, the term we've used before is the discount rate, right? And what the discount rate is unique from the interest rate is, I mean, I recognize there's a difference, but that's where that would come in, is you would say, so I know in Malawi, you have very high inflation compared to the United States, right? And so you would have to calculate that into your model that if you're trying to save money, it's a bad idea, right? What you should do is you should buy assets, right? As soon as you get money, you should buy euros or gold or land. I actually, I bought this bicycle and I went on Facebook Marketplace looking at bicycles, and a guy said, "Yeah, that's how I saved my money. I bought a bicycle to keep it so I could sell it later. Because if I put it in the bank, it's going to be gone because of the incredible inflation." Yeah. So thanks for that question. I hope, Rogers, that I answered it reasonably well. But that's, essentially I'm saying you're right. You need to include that in so my model calculates value in real, no, in nominal money, right? And that's a bad idea. You should calculate the value in real dollars, because in nominal dollars, your cost of electricity is going to grow every year because the money isn't worth anything, right? And so there's a couple things you could do. You could correct your model for it, or you could just say, no, we're going to work with dollars, American dollars or euros or something like that. And then we can we can convert it to kwacha some other time. All right. I'm glad that Rogers found my answer perfect. Thank you. Thank you. It's been a pleasure doing this. I'm really looking forward to meeting you guys because you're all coming to campus, right? I mean, can we have a party or something? Like we can go, we can have dinner or something like that. Yeah. Okay. I'll talk to Crispin about that because we should. That's the end of the very first semester of graduate study at Energy, right? That's reason to celebrate. Yeah. Okay, cool. So what I'm going to do now is I'm going to end the video.